Alright, let's look at what happens when you react an alkene with acid and water. Alright, so we have our water. H2SO4 is a really good acid. And what this is going to produce is it's going to create an OH group on the more substituted carbon of the double bond. So if we look at this double bond, we want to see which one's more substituted. This one's a secondary, this one's a tertiary. So what happens is this one's going to be the carbon that gets the alcohol. And we'll add a hydrogen from the acid to the least substituted. Alright, so let's see what this is going to look like. Let's draw the carbon framework just the way it is without the double bond. Now here on the more substituted carbon, we'll put our OH. And the carbon that was the least substituted got a hydrogen. And we lost the double bond. Alright, so when you see acid and water, what you should think is it's going to put an alcohol group on the more substituted carbon of the double bond. Alright, so this one's attached to 1, 2, 3 groups, so it's tertiary. This one's only attached to 2, so it's secondary. So we added the alcohol to the more substituted carbon. Alright, so now that we've seen what it produces, what the product's going to look like, let's look at the mechanism and see what actually happens. How did we get here? Alright, the first thing you should think is that the double bond is going to be our nucleophile. And what the acid does is it generates a proton. Right? So it's going to give us a hydrogen without its electrons. So these electrons are going to reach out and grab a proton. Right, when we do that, we can redraw our structure. And now that hydrogen is going to go on the least substituted of the two carbons. And the reason for that is because we're going to create a carbocation. And remember, carbocations always go on the more substituted carbon. Right? And if we think back about this carbon here is a secondary, this one here is a tertiary. So we're going to put the carbocation on the more substituted. Now what happens is your water is the nucleophile, and carbocations are really, really reactive electrophiles. So now the water can come in and add to the carbocation. And so if we redraw our product, or draw the next product, we have our carbon framework. We still have the hydrogen we added from acid. We still have the methyl group that's branching up. And now we have our water molecule that's sticking out here. It's only got one lone pair because we used one lone pair to make this bond. Right now, that means it has a positive charge. So the last step is the electrons from one of these hydrogens goes back on the oxygen, will generate H+, and this gives us our product. And that's why in the end, we're left with an alcohol group. And that's why we only typically need a catalytic amount of sulfuric acid, because we're going to regenerate that proton, that H+. And so we keep donating that H+ to the solution, so you only need a few drops of sulfuric acid. Let's look at the next one. It's a little bit trickier. Now, what happens here is you're still going to add an OH group, right? So when we see this water and sulfuric acid, is going to kind of yell out at us that we're going to put an OH group. Now, one of the thoughts is that we would have put the OH group here. But the problem is, we're going to get a carbocation intermediate. So after this has reached out and grabbed a proton, we get our hydrogen on the end, because that was the least substituted, and we get a carbocation here. And don't forget, there was a hydrogen that was implied from before. Now what happens here is you can do a hydride shift, because if you think back, carbocations, the more substituted, the better, right? So this is a secondary, this one's a primary, and this one over here is a tertiary. So if we can move this carbocation from a secondary to tertiary, that's really good. So what happens is these two electrons with the hydrogen are going to shift over, which lead us to the carbocation moving over one. The hydrogen we just moved is here. That initial hydrogen is still on that N carbon. And now that we've had this rearrangement, so this is called a hydride shift. Now the water molecule can come in and add to this carbocation. And so what that gives us as our final product is the OH on the more substituted carbon. Now, typically you only rearrange if you're going to move up in substitution, and it usually only works about a carbon either way, maybe two at the most in rare occasions. But whenever you get a carbocation, particularly if it's not a tertiary, you want to look to the carbons on either side of your carbocation and see, can I go up in substitution? Meaning, can I go from a secondary to a tertiary? If the answer is yes, then you can either do a hydride shift or a methyl shift, then you will get this rearrangement. So the big keynote that you have to take away from this problem is be really careful about rearrangement. All right, so we get the alcohol and the more substituted after rearrangement. Right, the hydrogen that was here shifted over, and our OH goes on the more substituted carbon. All right, let's try another one. Same idea. I think what we're going to see is that this is going to grab a proton. Right, the electrons from here are going to reach out and grab the hydrogen. And we'll draw the intermediate just because if we're looking at this, a good hint that this is going to be a rearrangement is anytime you have a secondary carbon next to a tertiary is a really, really good hint you're going to have a rearrangement. So we have that situation. There's a hydrogen that's implied. So we're going to do the same thing. We're going to do a hydride shift. This hydrogen will move over. We keep the carbon framework, but now we have a hydrogen that we've gotten from our acid on the end. We have the hydrogen that did the hydride shift in the middle, and our carbocation has now moved to the tertiary. Right? So essentially what we did is took our carbocation and went from a secondary to a tertiary. And anytime we go up in substitution, we feel like we've done a good job. And it's meaning it's likely to happen. It's going to occur. Now the oxygen from the water molecule will now be our nucleophile. Adds into the carbocation. As it adds into the carbocation, we're going to make a bond between the oxygen and the carbon that used to have the carbocation. So that's what this arrow is telling us. And so now if we redraw our product, we keep the carbon framework the same. And then our OH group comes off the more substituted. And that's our product. All right. Now, a couple of things you have to be careful about is anytime you have rearrangement, you've lost control stereochemistry. So if we'd made a chiral center, you'd get a racemic mixture. So be really careful about that. The other thing you can get is we did a hydride shift. You can also do a methyl shift. And a methyl shift would have a methyl group moving with its 2 electrons. All right, so the take-home message is when you see acid and water, you know you're going to get an OH. And it's going to go to the more substituted carbon, which is Markovnikov's rule, right? So it adds Markovnikov. The only problem is be careful about rearrangement.